Hi guys and gals. Today we are going to be finishing off our section on transformations with a little bit of symmetry. Okay, I've got two types of symmetry for you, something called line symmetry and rotational symmetry. I will say that as like an elementary school kid, I believe you guys have heard of symmetry before, right? Especially the type of symmetry you guys learned would probably be line symmetry. Okay, well, that was really weird. The type of symmetry you guys would have learned would be line symmetry. Um, what is line symmetry? A figure has line symmetry if the figure can be mapped onto itself by a line of reflection, a reflection in a line. Okay, and this is why this is tied into our transformations unit, because we talk about reflections and rotations and things like that. So symmetry, line symmetry. So as I said before, you guys have done this when in elementary school. Take a look at this first shape. Okay, I have a rectangle. Where would a line of symmetry be? Most of you guys would say down the middle, Miss Lee. But I'm going to say the middle. How? You got to be more specific, right? Down the middle. What do you mean? Someone might say, "Oh, down the middle, like a horizontal line," and I'd be like, "Oh, that's much better. That's a much better description, right?" So this is one of the lines of symmetry. And notice how it's a horizontal line. This is a line of symmetry because, and I'm going to go to my definition here, because the figure can be mapped onto itself by a line of reflection. What in the world does that mean? If I could take this rectangle like a piece of paper, if I could take it and fold it, right? Doesn't this top part, if I were to fold it down, map directly onto this bottom part? Right? If you take your piece of paper, a rectangular piece of paper, and you fold it right down the middle horizontally, you see that all the edges and all the lines line up. Okay? Okay, so that's one of my lines of symmetry, this horizontal line. Are there other lines of symmetry? And then somebody would probably raise their hand and say, "Yes, Miss Lee, down the middle the other way." I'm like, "The other way? What do you mean by that?" "Down the vertical side of this." And I'm like, "Oh, okay, good." And there we go. Right, I'm going to erase these old lines. We don't need these. If I draw a line down the middle here, if I take this piece of paper and I fold it down the middle going vertically, I can see that, again, my shape gets mapped onto itself. Meaning, see how here this, if you were to fold it, maps directly onto itself. So far I see two lines of symmetry in this rectangle, this shape. Are there more? And then I might hear someone raise their hand normally in class and say, "Yes, Miss Lee, what if you went corner to corner? Doesn't that work as a line of symmetry?" Okay, let's try that. If you were to take it and you were to fold it, yeah, this line here does represent me cutting this into two equal shapes, right? If I were to take this diagonal line and go across, I do end up with two of these congruent triangles. But is this a line of symmetry? And I'm going to say no, because if you take your piece of paper, try it right now at home. Take a rectangular piece of paper. If I were to fold this and map it onto itself, I actually am going to end up with something like this. And it looks like a kite, right? So that is not a line of symmetry. If you were to fold it, right, this corner would map to here, over here, and right, this side here gets mapped onto this side here. So diagonal lines, in this case, they are not lines of symmetry. All right. So here in this rectangle, yes, we do have line symmetry, and we actually end up with two lines of symmetry. And I can go back and redraw it just to have, two M's. Just to have my examples down in my notes, right? Two lines of symmetry, where are they? That would be this line here and this line here, vertically and horizontally. Okay? Actually, if I want to take a look at this shape down here, I know it's for rotational symmetry, but whatever. Take a look at this shape. It looks like a sun, right? How many lines of symmetry are there? There's a lot, right? I could draw a line of symmetry here. That's one line. Think about it. I can draw another line here. That's 2, 3, 4 lines of symmetry. Actually, believe it or not, there's more than just these 4 lines. Watch. What about if I were to fold it here between the rays, between those triangles? Wouldn't that map onto itself? Oh my gosh, so wait, let me go back. The original lines of symmetry, we had 1, I'm label 1, we had 2, we had 3, going through these triangles, right? We have 4 lines. And then if I were to go actually in between the triangles, here's another line. 1, 2, 3, 4. This is number 5, 6. I go through here, this would be number 7. And then if I go through these 2 triangles, that would be line number 8. And then there you go. Wow, this sunshine looking figure actually has 8 lines of symmetry. Pretty crazy. Okay. All right, so there we go. Anyways. All right, the other type of symmetry is rotational symmetry, as you see here in the notes, right? Oh, why does it do that? Go back. I just want to highlight you. Oh, nope. Okay, sure, whatever. Rotational symmetry. All right, rotational symmetry, what is it? As you can see in the notes right here, it says a figure has rotational symmetry if the figure can be, and there's those words again, mapped onto itself by rotating the figure less than 360 degrees. Okay, why does it say that specifically, less than 360 degrees? Because anything can be turned 360 degrees and be mapped onto itself, right? Isn't 360 degrees one full circle, right? One full turn. So obviously you can turn any shape 360 degrees and you map it back onto itself. So that doesn't count. So rotational symmetry is when you have something that can be mapped onto itself by rotating it less than 360 degrees. In this case, when I look at this sunshine, I can do that. So let me see. I'm actually, and this is why I'm in Word here, I'm actually going to try something different here. Let me stop inking. Let me erase that. I'll go back to inking. Just kidding. Working with new technology here. All right, there we go. What if I take this sunshine? I'm going to duplicate it. So let's see, Control C, Control V. Oh, that didn't work. I want to duplicate it. There we go. Okay, so I have 2 sunshines here, right? Map back onto itself means it needs to line up perfectly. See now how I have these 2 sunshines? They're perfectly mapped onto each other. In fact, what if I take this and let me change the color. Let's change it to orange. Hey, all right, cool. So I have 1 orange sunshine and 1 blue sunshine. Mapping back onto itself means the shape is going to look exactly the same. So what's going to happen here is if I take this and look at when I rotate just from that much to there, stop. See how we've mapped this figure back onto itself, right? Let me go back there. Let me turn it back, right? Here's the original sun. All I did was took this and rotated it just that much. That's not a whole lot, okay? So if I think about what I did, let me get my pen now. I took this and I rotated it just that much. But the question is, how many degrees is that, right? How many degrees did I turn? Now, if I could, and I take like a protractor and I go to the middle here and I create this angle, I could measure it. Whoops. But I don't have a protractor. I can't measure this. So one thing you could do is kind of think about how many times are you going to rotate till it gets mapped on by itself, right? So for example, if I stop it again, right? If you think about it, I can do this multiple times, right? So let's see, like 1 turn, 2 turns, 3 turn, 4 5, 6, 7, and 8. Notice how there's 8 total turns before I map back onto itself. That means, if you think about it, right, we had 1, 2, 3, 4, 5, 6, 7, 8. Didn't we say if I went all the way around in one whole turn, that's a whole 360 degrees? Well, what if I took that 360 and split it up into 8 equal turns? In other words, what if I took 360 and just divided it by 8? What do we get out of there? And so 360 divided by 8 would be 45 degrees. Each of these turns is a 45-degree turn. Aha, so there we go. That's kind of cool to know, right? And you can go all the way around the shape. Each of these is a 45-degree turn. So what I could say is, yes, this shape has rotational symmetry, okay? It has a rotational symmetry, and if I wanted to be more specific, this has rotational symmetry of 45 degrees, okay? And so there we go. Meaning, actually, I can talk about each of these turns. If I do one turn from the very beginning right here at the top, if I turn once, that's 45 degrees. Meaning, this is 90 degrees. And this would be, let's see, 135. And then if I go from here to here, it would be 180, and so on and so forth. I can actually say that it has rotational symmetry for each of these. And just keep going 45 and keep adding 45, okay? But the smallest turn, we say it's of 45 degrees. So 45-degree rotational symmetry. All right, so here we go. I've got a couple examples here. I've actually got 3, but I'm just going to do 2 at a time right now. The first thing I want to do is determine if the figures have line symmetry, rotational symmetry, or none. Actually, I can add in a third option here. It could also have both, right? So you can have line symmetry, rotational symmetry, none, or both. If the figure does have line symmetry, you need to describe how many lines there are. And if it has rotational symmetry, describe the rotations. So I'm going to start with figure number 1 here. It's this hexagon. Does it have line symmetry? Actually, yes, it does, right? So what I'm going to do is, let's take a red pen. Yes, it has line symmetry. And let's draw the lines. Now, if I had drawn a line, let's start here. Vertically cutting this shape down the middle here, there's one line of symmetry. Actually, notice how I cut the shape in half by going through the sides? Couldn't I do the same here, going through these sides and these sides here? So that's it. 1, 2, and this one's super crooked. Let me draw a better one. Come on, pen. Oh, it doesn't want to work. 3 lines of symmetry. But actually, there are more than just these 3, because I actually have, what if I went from corner to corner? There's another one. Oops, that was horrible. 1, 2, 3, another 3. So what is that? 1, 2, 3, 4, 5, 6. Right? If I drew back the other lines, you would have 6 total lines of symmetry here. So the answer to the question, yes, it has line symmetry. Line symmetry, actually, I'll do this. I'm going to write this as 6 lines of symmetry. Okay, let's answer the next question. Does it also have rotational symmetry? And yes, it does. If I could take this shape here, let me see if I can select the object. Yeah. See, I can take this, and if I could rotate it right there, there's 1 turn, right? 2 turns, 3, 4, 5, and 6. Notice how I went all the way back to the beginning again because my mouse, my cursor was here. I started here and I needed it to end up there. Notice how it took 6 different turns for me. So this hexagon, let's see, 360, get my pen back. 360 divided by 6 would be 60. So yes, this has rotational symmetry. We would say it has rotational symmetry. Rotational symmetry at 60 degrees. Okay? In fact, each turn, there would be 60, right? And then 120, and then 180, and then, let's see, 240, 300, and then back to the beginning again, right? So each turn at 60 degrees. So actually, this shape has both. All right, number 2, what about this letter R here? Let's see, this capital letter R, does it have any line symmetry? Is there any way for me to fold it? No. Where the left side and the right side are map onto each other, basically like a mirror image. Looks like no line symmetry. Does it have any rotational symmetry? Let's see. If I could take this, see, I get to be able to take it and rotate it, and I don't think so. So why did it select that? I want to select this shape. Here we go. Right? No, I don't think so. So, all right, it has no line symmetry, no rotational symmetry as well. None. No symmetry. Letter Z. Okay, so first of all, I gotta ask myself, does it have line symmetry? And I know what you're thinking, like, oh, just cut it down the middle, Miss Lee. Both the left side and the right side, top and bottom, are the same. But no, it's not a mirror image. Look, if I were to take this and if I could fold it down to here, that does not match up, right? So this has no line symmetry. I could try here. What if I folded it here? No, right? It does not fold up correctly. This has no line symmetry. Does it have rotational symmetry? Yes, it does. How many degrees, though? So let me see. It's easier because I can take this object and rotate it. But let's see. Remember, it has to map onto itself, meaning I'm going to rotate it until it looks like the same thing again. So here's this letter Z. If I took this and rotated it to here, well, that's not a Z. Oh, there we go. We've got it back to itself again. Let's see. I went from the top to the bottom. How many degrees is that, right? If I went from, let's see, get my pen, come on. So if I went from the top to the bottom, how many degrees is that? That's a half turn. Half of 360 is 180, right? And if you think about it, there's really only 2 turns. So if I wanted to go back and do that thing where I just take 360, in this case, it takes 2 turns to get it back to itself. So 360 divided by 2 is 180. So I'm going to say yes, it has rotational symmetry. Rotational symmetry, I'm going to abbreviate here, at 180 degrees. So no line symmetry, but it does have rotational symmetry.